Formalization of Dialogue in the Decision Support System of Dr. Watson Type, by Saveli I. Goldberg and Vladimir Sluchak, introduces a novel approach to formalizing dialogue within decision support systems. The authors aim to enhance the efficiency and effectiveness of these systems through the development of a structured dialogue framework. Decision support systems play a crucial role in various domains, particularly in healthcare, where accurate and timely decisions can significantly impact patient outcomes. Dr. Watson, a question-answering computer system, serves as an exemplar of such a decision support system. The main contribution of this work is the formalization of dialogue between users and the decision support system. This is achieved through the creation of a dialogue model that captures the structure and flow of conversations. The model is based on a set of predefined rules and patterns, allowing for more efficient and effective communication. The authors also discuss the challenges associated with natural language processing in these systems, including ambiguity, context, and common sense. They propose the use of semantic role labeling to better understand the meaning and intent behind user queries. Furthermore, the paper explores the integration of domain-specific knowledge into the dialogue model. This involves incorporating expert knowledge and best practices from relevant fields, such as medicine, to improve the accuracy and relevance of the system's responses. In addition, the authors touch upon the evaluation of the proposed dialogue model. They suggest using metrics such as response accuracy, user satisfaction, and system usability to assess the effectiveness of the formalized dialogue approach. Finally, the paper concludes by discussing potential future directions for this research, including the development of more advanced dialogue models and the application of this approach to other domains beyond healthcare. Overall, this paper presents a significant contribution to the field of decision support systems, offering a structured approach to formalizing dialogue and enhancing the efficiency and effectiveness of these systems. The system-user interaction process for DWS commences with setting goals for the desired outcome and the user's care plan. Subsequently, the system influences decision-making by organizing and presenting data or asking clarifying questions. Ensuring the confidentiality of specialist-machine interaction, providing alarms in situations of obvious errors, and including game elements in the interaction between the user and the system are essential. A convenient, efficient, and friendly user interface is also crucial. Evaluating and refining user solutions is fundamental for DWS, which implies the generation of internal DWS solutions at certain steps of the user-machine interaction. If a DWS-generated solution doesn't match the one by the user, DWS attempts to influence the user to reconsider by presenting questions generated by DWS at each step of the decision-making process. The DWS decision-making process can be formalized as branching into two sub-processes running in parallel and exchanging information at certain points of their trajectories. This technique has proven to be effective and is widely used in machine computations. In our case, one subprocess runs inside a machine and another one in a human's mind. The exchange of information is organized in a way that facilitates fast conversion of the process. The system does not show its internal solutions. Instead, it presents them to the user implicitly with questions that should stimulate a fast thinking process in the user's mind. This feature should contribute to the effectiveness of the system. Implicit, intuitive thinking is not commonly attributed to a machine, but the characteristics of this type of fast thinking are used in DWS when analyzing user input and generating questions. Another important feature of DWS is the ability to store the history of previous decisions and errors, analyze and generalize the causes of errors, and effectively present this data to the user at any step of the decision-making process. While presenting the history of previous decisions and errors, DWS requires the user to assess the prognosis as a result of the selected actions. If the reality differs from the prognosis, the user is given the option to explain the discrepancy. The necessity of explaining the failure has a positive effect on the quality of the decisions in the long run. The DWS process schema reflects the main states, actions, and transitions of the process. In particular, the branching into two subprocesses is seen at the first step, just after the parameters input, and the very intentional inequality of information exchange is reflected in the box where DWS machine computes its internal solution hidden from the user. The DWS process schema, as depicted in Fig. 1. Illustrates the user DWS dialog localized within the 5 central boxes. This dialog encompasses various scenarios that cover all cases of the decision-making process. Firstly, DWS highlights inconsistencies between the user's decision and the parameters upon which it was based. This prompts the user to reassess their choice in light of new information or perspectives. Secondly, DWS indicates the presence of additional information that could potentially alter the user's decision. This encourages users to consider a broader range of data points before making a final decision. Thirdly, DWS identifies potential distortions in input data, which may lead to incorrect decisions. By flagging these distortions, DWS helps ensure that decisions are based on accurate and reliable information. Fourthly, DWS locates precedents and asks the user to analyze them. Users can also add precedents to the history, further enriching the decision-making process with past experiences and outcomes. Finally, the last scenario is designed to capture any additional problems or precedents not stored or discoverable by the machine algorithm but directly provided by the user. This ensures that the DWS process is comprehensive and adaptable to unique user experiences and insights. In summary, the DWS process schema provides a structured framework for facilitating informed decision-making through an interactive dialogue between the user and the system. By addressing inconsistencies, providing additional information, identifying data distortions, utilizing precedents, and incorporating user feedback, DWS aims to enhance the accuracy and reliability of decisions made within complex problem-solving environments. In the context of the DW-SUSER dialogue, a formal description is presented, focusing on the vector of parameters and its components. A vector X is defined as a collection of n parameters, each being a name-value pair with values that can be continuous, categorical, or descriptive. The space of all such vectors, X, has a dimension of n. The concept of subvectors and proximity in the metric space X is introduced, along with the notion of syndromes and antisyndromes for a subset A of X. A minimal antisyndrome of A is an antisyndrome such that any subvector of it will be a syndrome of A. The minimal antisyndrome plus any other parameter is also an antisyndrome of A, and excluding any parameter from the minimal antisyndrome makes the remaining parameters a syndrome for A. A decision-making function f, x, maps the space X to a set of possible solutions, alpha I, and the class of alpha I is denoted as A, alpha I, f. Each solution alpha has a typical representation or vector S, alpha, in X, which can be provided by experts or obtained from the median values of parameters in the training sample of A, alpha, f. This formal framework aims to facilitate the understanding and processing of complex user dialogues within the DWS system. The DWS machine engages in a dialogue with the user, posing questions and receiving responses. Prior to this dialogue, the user provides their solution, denoted as alpha U, and a vector of parameters, v equals v1, vm, based on which they arrived at their solution, f user, v equals alpha U. The DWS machine has access to FDWS, x, for any x in X, a set of minimal antisyndromes of A, alpha j, FDWS, for expected solutions, alpha I, and a set of typical representations of parameters as S, alpha j, equals, S1, alpha j, S2, alpha j, Sn, alpha j, for any alpha j element of alpha I. The basic scenarios for a dialogue between the DWS machine and the user are described in detail below. During the dialogue, the user can change both input data and decisions. Scenarios may change accordingly. The user solution will be denoted alpha U, DWS machine solution will be denoted alpha W. Algorithms for local explanation, such as LIME local interpretable model agnostic explanations or Shapley additive explanations, play an important role in our process, especially those that assign weights of importance to the parameters for a given solution. DWS shows the inconsistency between the user's decision and the parameters based on which he made the decision. It is assumed that the dialogue begins with the announcement of the user decision, alpha U, and vector of m less than equals n parameters, v, based on which this decision was made. For example, the user describes his condition as slight general aches, sneezing, small headache, stuffy running nose, no cough, airborne allergy in anamnesis, and his diagnosis is a relapse of airborne allergy. DWS machine checks if this set of options matches the selected solution. For this, the presence of antisyndromes of A, alpha U, fuser, is checked. If antisyndromes are found, they are presented to the user for analysis. In our case, slight general aches and small headache is a minimal antisyndrome for airborne allergy, so the user changes his diagnosis to cold and DWS does not find the inconsistency. The figure illustrates the domains for the user solution alpha U in a space of two symptoms, x1, x2, with numeric values. Each point in this space represents a syndrome or an antisyndrome. The domain defined by the user, A, alpha U, fuser, overlaps with the domain defined by DWS, A, alpha U, FDWS, which is bounded by the area of minimal antisyndromes. For each vector versus x1, x2 that enters the area of antisyndromes, the DWS machine will highlight inconsistencies between versus and alpha U. The DWS machine indicates the presence of additional information that may alter the user's decision. If the information in the subvector V from M parameters, M less than N, is consistent with the user solution, DWS machine attempts to check for any additional information that could change the user's mind. It finds all vectors VSD equals V, SM plus 1, alpha D, SN, alpha D, for all alpha D element of alpha J, where S, alpha W, is a typical representation for alpha W. If a case is found where FDWS, VSD, equals alpha D and alpha D does not equal alpha U, a local explanation of the VSD decision is sought. In the example provided, high fever and extreme exhaustion should change the diagnosis from cold to flu. Based on local explanations, DWS machine identifies the most important parameters not provided by the user and poses questions about their importance. In this case, the first question is about fever, and after the user responds, they can either maintain their decision or change it. The next question from DWS will be about extreme exhaustion, and if the answer is no, the diagnosis of cold remains. The seventh page of the research paper delves into the domains of solution vectors in the space of two variable vectors of parameters. Specifically, it focuses on an initial vector x1 with m parameters and an additional vector x2 with nm parameters. The DWS machine assesses whether additional parameters can alter the user's solution, employing a local explanation method, such as LIME, to generate questions on the importance of these parameters. Moreover, the paper highlights that input data could be distorted, leading to false decisions. Therefore, the system checks whether such distortions can affect the user's decision and asks for clarification on the dangerous parameters if necessary. For instance, in a case where the data indicates a temperature of 38.0, headache is moderate, and exhaustion is small, the system may ask to recheck the temperature if it could potentially alter the decision. Furthermore, the DWS machine randomly selects vectors from the proximity of vector V, where FDWS, x, equals alpha D and the solution alpha D does not equal alpha U. It then seeks a local explanation for the selected vector XDWS, which has the minimum value of the metric delta, x, V. The system asks questions about the meaning of the most sensitive parameters in this explanation, possibly concerning the refinement of parameters already present in versus or not yet involved in the description of the case. In conclusion, this page emphasizes the importance of checking for potential distortions in input data and ensuring that additional parameters do not alter the user's decision. It also demonstrates how the DWS machine utilizes local explanation methods to generate questions on parameter importance and seeks clarification on sensitive parameters to ensure accurate decision-making. The DWS machine learning model is designed to enhance decision-making by analyzing and explaining potential errors in user solutions. It utilizes a local explanation procedure to identify the closest point with a different decision, enabling users to understand the implications of their choices. DWS also collects precedents and asks users to analyze them, requiring them to explain errors and predict consequences of their decisions. This process improves the quality of solutions over time as users reflect on their mistakes and understand discrepancies between their predictions and reality. The explanations provided by users are collected, analyzed, and presented back to them in various forms, including a summary table of error descriptions and warnings about possible errors. These warnings are generated based on the most probable errors in similar situations, considering measurement errors, parameter evaluations according to the norm pathology scale, and differences in informational weight of parameters. Users can filter and sort these entries according to their priority, enhancing the decision-making process. The paper presents the development of a Dr. Watson-type AI system, an advanced decision support system designed to identify and mitigate potential errors in patient management. This system learns from past mistakes and provides insights for future improvements. The authors emphasize the importance of understanding error causes and prevention strategies. They propose a bidirectional adversarial explainability approach, involving both forward and backward analysis of decision-making processes. This approach identifies potential pitfalls and improves decision support system accuracy. The paper also highlights the role of human intuition in decision-making, citing literature and psychology examples. It emphasizes the need for a balanced approach combining human judgment with AI-driven insights. The authors reference various studies on decision support systems, including passive decision support for patient management and explicit and implicit decision-making strategies. They discuss the importance of transparency and explainability in AI models, referencing works on interpretable machine learning and model predictions. The paper concludes by discussing future perspectives of robotics and AI, including ethical considerations and potential risks. It emphasizes the need for continued research and development to ensure AI systems are designed with safety and efficacy in mind. Overall, the paper provides a comprehensive overview of the Dr. Watson-type AI system, highlighting its potential benefits and challenges, and emphasizing the importance of interdisciplinary research and collaboration to create effective decision support systems that can improve patient outcomes.